Hello, everyone. I think Kasia presented us briefly in Polish. I didn't understand much of that, so me and Venti are going to cover this real quickly in English as well. Overall, we are working for SoftServe. This is a company that specializes in cutting-edge IT consulting, and we are part of the operational field working in cloud and DevOps. And we cover all sorts of cloud and DevOps stacks for a variety of customers from all sizes and all industries. A bit for ourselves. Venti, can you please introduce yourself?
Yeah, thank you. I'm a Devops Architect in SoftServe. I have more than 20 years of IT experience. I started as a software developer. Then I switched to Unix and Linux system administration and gradually proceeded to DevOps engineering and later architecting roles. I actually graduated from physics a long time ago, which I believe helped me a lot with the overall mindset. And my relevant certifications, I'm a Google Professional Cloud Architect as well as AWS Solutions Architect at professional level. So that's all from me. Ogi?
On my end, I'm Ognian. I'm a senior DevOps engineer at SoftServe. Over the past roughly 10 years, I've been working in various fields in IT, covering areas like web design, system administration, even some more process-related roles like project management and process management. Over the past few years, I'm focusing on DevOps because this is what I think really makes a difference nowadays, and this is what makes big corporations able to cut down costs and thus be able to basically deliver competitive product. In the past, my first university degree is totally non-related, but afterwards I focused on informational system and technologies with my latest master's, and then I got several certifications which I think helped me a lot with my current role as a DevOps engineer. So what we're going to be talking about today is the phase 2 transition to immutable infrastructure. I'm fairly certain that some of you did not participate in the phase 1 discussion a couple of weeks ago with SysOps Polska presentation. So we'll be doing a very high level overview of phase 1 as well in this course so that the newcomers will not feel completely off the grid. After we are going to cover what we did in phase 1, we're going to outline the necessities to do phase 2 of our project. We're going to describe the different stages that we needed to go over and the main challenges we needed to solve. And we're going to describe the final stage and what are the things we did to solve our challenges. And hopefully this is going to be beneficial to you guys. As long as with phase 1, Venti, can you please cover our approach here?
Yeah. So the goal was to modernize an existing application, which is a product of a a product which consists of multiple components which act together with machine learning to actually process different types of human-generated data, so to say. So it's text, free-form text, audio, etc. And they process it for specific patterns and specific information which can be accumulated and aggregated for the customer's needs. The plan was to provide a hosting environments for multiple clients of our customer. And in order to achieve that in practice, we had to transform their legacy infrastructure architecture to immutable infrastructure components with cloud managed resources as much as possible. That was phase one. And the phase two actually focuses on transforming the virtual machine-based deployment to container-based using Google Kubernetes engine. And this, in addition to that, it also adds new components and new features to the existing solution, which are directly deployed in Kubernetes. Okay.
Okay. So to illustrate what we just said, we are going to show you two diagrams, before and after diagram. Those of you guys that were on our previous presentation already have seen those diagrams. Long story short, if we consider this to be the very, let's say, high-level architecture of the application itself, phase one consisting of making sure that the state of all those services are logically abstracted away from the hosts so that the services can be orchestrated in terms of infrastructure in a bit faster manner. This is where we got at the end of phase one. So we have every piece of immutable infrastructure being orchestrated by Terraform and Terragrant, and pretty much a deployment of a new version of any of the pieces from the application consisted of wiping out the given servers and reinstating new servers here. This all was made possible with Terraform, which is being controlled by Jenkins pipelines. And for any sort of post-installation activities that needed to happen on the servers, we used Ansible in, let's say, some sort of a masterless or even serverless manner, because the Ansible engine itself was running on Google Cloud App Engine. And this is where we went, basically, from having manually or deployed through configuration management workloads to static servers to dynamically deployed individual servers hosting everything. And this is basically where we stand when we developed the plan and the necessities for doing phase two. This is basically what it consists of. Fancy?
Yep. So all of this came from the necessity. It wasn't just decided on a whim. First of all, the major switch from batch processing with Hadoop jobs to stream or event-based processing, which is performed by custom components. And it was decided that these components would scale better and would work more efficiently in a container environment, in containerized environment. In addition to that, it helps a lot with cost management, because a containerized environment is much more effective from the cost perspective compared to multiple separate virtual machines. Each has a large overhead and much slower boot times, which makes the maintenance much longer. Whenever we need to perform updates, it takes hours compared to minutes with a containerized environment. And this brings more possibilities to enforce immutability, which is the very nature of container technology, and was very hard to achieve in a VM based environment. Okay.
Okay, we want to add here that basically, even though that we're looking into this problem from infrastructure management perspective, it should be noted that the decision to containerize an application like this and let's say the major legwork still comes from programming perspective, because overall the software architecture needed to be drastically changed for this to be accommodated. So if we items 2 and 3 from this list are really, let's say, a bit of a bonus compared to number 1. Overall, our clients really needed to make sure they can process events faster in real time, and we have all the multiple advices given from cloud vendors when it comes to transitioning and re-architecturing your application for a major transition like this. First of all, the so-called stage 1 was making sure that all the additional features and components which are somewhat decoupled from the major application pieces are added as microservices, and they're added to the existing virtual machine hosted application by networking means without actually touching the other part of the application. With this, we have achieved 2 main objectives. The first one is doing some sort of a proof of concept on the containerized services and showcasing to our clients that this is actually working. It's cost effective, it's fast, and it's stable. On the other hand, we have proven that we can add additional features in a much seamless way than we do now. And usually, instead of needing to schedule big maintenance windows to promote a given change or add a new feature that, even though affects one piece of the infrastructure, can lead to instability across the whole environment for one reason or another. This can just go in there in pretty transparent manner. So stage 1 was adding few features that served as let's say some sort of a blueprint for how the main application will look in this architecture. Stage 2 consists of replicating the minor feature architecture to the whole application and its wholeness and all the different features that it offers to the clients. It should be noted that during stage 2, we did not mean to replace the existing application, but rather get an environment that can run in parallel to the old one. This basically allows the clients and their clients to environments simultaneously in terms of processing workloads in the new style and the old style environment. This showcases first the speed of the new architecture, and second, different bugs and missing features and all the qualities of any project that is a work in progress have been isolated to a shortlisted, let's say, pilot projects. This was to make sure that the actual transition will happen with very little risk. And during stage 3, eventually,
So I think we might have some issues.
Yeah, some problems with internet, yeah?
Yeah, probably. Let's give only 30 seconds, I believe.
Yeah, of course.
So to recap, stage 2 is what was the last discussed. In addition to the existing legacy so-called environment from the from what we discussed during the first presentation. We have a parallel Kubernetes deployment, which on one hand performs its own processing, or its own part of the processing of the customer data, and adds new features which didn't exist in the previous application architecture. And stage 3 is something we are yet to reach, is to perform all the processing and and funnel all customer traffic through the containerized application, remove all dependencies from the legacy infrastructure, and eventually decommission it. So this is from stage 1. We have in parallel to the legacy environment, which is at the bottom, we have a GKE cluster with several node pools. We have a number of applications deployed there. We have front ends with a number of entry points accessible by customers or by external applications. We have Kafka message processing together with Zookeeper for service discovery, Minio, some custom components, and monitoring, which uses Prometheus for metric collection, and it's integrated with our current centralized monitoring solution. In order to achieve access to this environment, we have a dedicated Bastion server, which is only accessible through our Zero Trust access management solution. And all that works in parallel with the current environment, as I already stated. So stages 2 and 3. Ogi, are you back?
Yes, I'm here.
Okay. Do you want to continue?
For some reason or another. Apologies for this. Okay.
No worries.
So
if you want to add anything here,
I think that I think that we're good now. For stage 1, we can proceed with second stage. So here in the second stage, you see that basically all the rows from the old architecture are replicated in this layout here. If you see this Memex, the minor application that was added to the infrastructure in stage 1, basically we have all the different endpoints set up as a separate Kubernetes deployment. And the color coding in this diagram means the following. All the red stuff is proprietary, and all the other, the white stuff is something that's open source implementation that can be easily containerized. You see the names of various components. Some of them are related to the logical workflow of data, and some of them are related to the management. For instance, Kafka with Zookeeper ensures the on-time processing of real-time events and storing them to the corresponding decisioning engine. On the other hand, tools like Helm and Prometheus are used mostly for management and for ease of deployment. The biggest challenge with Kubernetes in this specific case is making sure that we have good place to store the data, because by design Kubernetes pods are stateless. So this is why we have logically divided this workflow into different node pools. The one is the ephemeral and the other is the persist one. Besides using Google Cloud Buckets, which are the default storage for objects, there are multiple containers which, through the use of persistent volume claims, use persistent storage for their data. This mostly covers the Elasticsearch objects, which need to persist for months after a given decision is made on a given data set. All the pieces that are marked in green basically mean that at this point they cannot be containerized, because we are talking about third-party solutions, being proprietary or open source solutions, which really aren't, let's say, container ready for one reason or another, and cannot be containerized by means of purely DevOps means. They require some programming changes, which are not part of the scope of this project. Benji, can you add something else for stage 2 and 3?
Yeah, we had to be very careful here with regard to data security. First, who and under what conditions can access the environment and specific data storage objects. That's why we use this Zero Trust Access solution by SSH.com, which were the developers of the original SSH software. It's named Privix. And through it, we can ensure that this environment is only accessible through the Privix interface, which provides either SSH access or web access for the web endpoints, and in some cases remote desktop. But since we don't have any Windows machines here, it's only used to simplify some access requirements. And of course, all data is encrypted both in transit and on disk. That is true for the cloud storage objects, for the Cloud SQL. Here we have containerized MySQL, but that's more like a temporary solution until we manage to migrate the database to the cloud managed service. And that's also true for the disk volumes as well. Okay, let's continue. So the main challenges to solve first was with the mindset of the stakeholders. In general, a containerized environment is something new for most of the people in the company, I mean, in our customer company. And there are a lot of practical differences when one needs to access, manage, update, or secure a containerized environment compared to something which is fully based on virtual machines. The access security controls for developers and clients had to be done in a way that on one hand provides sufficient access without too much effort on the client side, but without sacrificing the security requirements. The monitoring is something which is, again, very different in the way it's implemented from a server to a container and the containerized application. And the stateful components, which cannot easily be containerized, they had to be well, properly integrated with the new infrastructure. So that, well, on one hand, everything had to be carefully planned with regard to what can be containerized at what point. And on the other hand, we had to stick with some legacy infrastructure for the time being. Okay, probably you have something else to add here.
I think that the main challenges indeed were related to the mindset of all stakeholders indeed. So probably we can proceed to the next step. Okay. So the final state of the infrastructure allows us to have flexible and easy to scale solution that can provision resources to applications exactly as they're needed without any over provisioning. And this, let's say, covers the majority up to maybe 90% of the all services consisting of this application. This way the client has saved a lot of money and has boosted productivity across their estate. Of course, we need to point out the existence of a few components that need to be hosted on VMs until they're being replaced. We're going to cover them shortly as well. All of them are developed and provided by third parties, which offer support only for their software being hosted on a cluster of virtual machines. If we can go back to the diagram, Venti, this, as I said earlier, this covers all the objects in green, the SFTP solution, and items like Tableau and Airflow. And this is how this challenge is being handled currently. While Tableau itself is not going to offer any containerization in at least in the next few versions, we have already made some steps around containerizing Airflow, and hopefully in the next month it will be a fact. But for the time being, this greatly illustrates the situation in which you have fully containerized microservice architecture, which needs to connect and work with a service which is out of it. So far, it works great, and the overhead of this being in a virtual machine doesn't contribute to the overall cost. So I think it's safe to assume that the few items marked in green may remain in their legacy state at least for the next half a year.
Yeah, just a minor note here, since SFTP is not very clear, it's not just a base implementation of something like OpenSSH, but it's a commercial third-party product which has a number of features which are required on top of the basic SFTP service. And that's something which we can't easily containerize at this point without the vendor's support. Okay, back to this stage, to this slide. Yep.
Okay. So around the challenges that we faced and successfully solved, of course, there are a great many of them. We have outlined just a couple because we're tight on time for this presentation. So the first one was the modular deployment of microservices. We have used our existing Ansible role structure, which we used in the past to orchestrate our services on top of the virtual machines, to orchestrate a given set of Helm charts in roles instead of deployment on virtual machines. This allowed for seamless transition to the old to the new infrastructure, and of course it required some refactoring of the code, but to the very least our logical continuous integration pipeline did not change in very radical fashion. So from DevOps perspective and from infrastructure support perspective, the changes weren't very critical, besides just changing the contents of a given rows, adding new rows, and all that kind of stuff. We also implemented some new Google Cloud Storage buckets for ephemeral data processing. This was a requirement from the application. In the past, we used only a subset of buckets for different roles. With this architecture, we actually doubled the number of buckets. The good thing about the cloud provider, like Google in this case, is that they allow for lifecycle management of data in buckets, and this really allows for making sure that the data is existing on the bucket for only for the period in which it's allowed to be there. There are things like auto archiving, archiving based on timestamps, and all that good stuff, which is really useful when you're dealing with large volumes of ephemeral data. The other thing related to security is integration of the Kubernetes management interface with PrivX. It was a bit of a challenge initially because as monitoring security in Kubernetes world also revolves around some new paradigms which aren't really applicable with securing your virtual machine access. In this case, we have solved this problem by exposing Bastion hosts, which has all the required Kubernetes, Helm, and Docker toolset that's required to work with the whole cluster, issue commands on it, do troubleshooting and all that. But this server itself is, the access to it is protected with PrivX, which fulfills the requirements of the role. We have to have a reliable management interface, and we need to secure it properly. And this is something that we have architecturally accomplished, but technically we're still implementing. This is the integration testing that is this point run manually, but it's a matter of time before it's actually automated and being able to run on schedule. Maybe Vance, you can elaborate it a bit more.
Yes, since there might be some questions here. Here with Ansible, we have this unified approach that all the code base is in Ansible is put together in a single place, and the tasks, the configuration tasks, and all the variables are applied according to the server role, which, well, usually it's the application role, but with the legacy infrastructure, we have a single server with a single application. And basically, whenever a server initiates an Ansible run for itself, then a single role, a single Ansible role is matched to this server, and the correct variables and tasks are applied to it. With Kubernetes, we used a similar approach, but we have a number of Kubernetes-related Ansible roles. So a single cluster can have a number of different applications, and they are defined at a higher level. So we have one set of components as a single entity deployed in Kubernetes. Then we have another set of components as another entity, and for each one of them, we have another a different Kubernetes role defined, which is automatically applied to this cluster. With regard to the ephemeral data in the legacy infrastructure, we had to rely on Hadoop's distributed file system, which had its limitations. So on one hand, we had to provision sufficiently large HDFS, which in some cases was several terabytes large, to process data in large chunks once or twice per day. Here, on one hand, we perform event-based or stream-based processing. So this processing is performed throughout the day, which reduces the load on the infrastructure on one hand. On the other hand, all the ephemeral data which gets generated during processing can be stored in GCS buckets, which automatically removes the disk size limitations we had before. With regard to the management interface, well, now we, in addition to the server level access, we have cluster level access for Kubernetes, where only a limited set of Kubernetes specific tools is exposed to the customer, and eventually when we have multiple clusters per environment, depending on the role of the user's role in our zero trust solution, only a specific cluster can be accessed. With regard to the automated integration testing, well, we actually have automated testing, but we perform it regularly against the test environment where we run our full continuous integration and all the tests. So we test our images, our Ansible code, and all the orchestration in a single place using this automated testing platform. So this is how our deployment pipeline looks like. Well, at least it's a good approximation of it. We use Jenkins, a single master for all environments, and one Jenkins slave per environment. So from the master, we initiate the master playbook, which ensures that we have all the fresh images built using Packer. It updates the image definitions in our Terraform code and runs Terraform step 1, which actually provisions a new environment if it doesn't exist, or updates the main project and networking components. So it creates eventually a new project, a new VPC, or updates some VPC resources like networks, subnets, firewall rules, etc. And it creates a Jenkins slave in this environment if it's not already there. And then the Jenkins slave initiates its own Ansible playbook, which orchestrates the deployments in a specific order. So we deploy the app engine, which contains all of our Ansible code. Then it provisions the GKE deployment, and then it proceeds with the legacy deployments, which are steps 2 to 5. Actually, we are working on parallelizing these deployments so that we don't have to wait for GKE to finish in order to start with the next steps, it's relatively straightforward to achieve using Ansible. And then we run an optional app engine Ansible apply from the app engine, which is an additional way for us to ensure that all the code has been correctly applied against the newly provisioned resources. And after all of this passes successfully with no errors, we have our checklists, which consist of a number of application and service-specific tests. So for each of the service components, we have at least one Ansible task designed to check its status. In most cases, we have several tests and something else which is planned is to initiate additional application-specific checks using Airflow DAGs. And one more thing, we have developed and implemented for each test environment, we have the option to run an automated smoke test, which actually performs a test, a full-blown test processing using a test data set. And we rely on all of these steps to run successfully in order to be able to say, well, our current version of the code and our current images, our current Ansible, everything works as expected. I think that's all. Ogi, do you have anything else to add here?
Yeah, when it comes to this workflow, I just wanted to point out that this illustrates the transition between stage 2 and 3. You recall stage 2 was introducing the parallel workload in Kubernetes, and stage 3 was decommissioning the old one. Mm-hmm. So if you use this diagram as a blueprint, accomplishing stage 3 is as simple as removing some of the items on the last column. Yes. Whenever they are not ready. So this is how seamless it is actually. At a given point, we are just going to have the G-key deployment option running after having the master playbook. The master playbook completes the network, and all the other components which are built over the network, including Kubernetes, are pretty self-sufficient. So
yeah, probably as an actual example here, when we have a confirmation that the Airflow containerization is ready, we just update our Kubernetes Ansible role to deploy Airflow if it needs a separate Helm chart, or if it's already added to one of the existing Helm charts, we just need to reapply Ansible, and then we have an Airflow deployment in Kubernetes, and then it's just a matter of feature switch in Terraform to turn off the Airflow deployment in the legacy infrastructure, which will, in the Terraform run, remove the current Airflow instance. And a similar approach can be used for the other legacy resources. Okay, I think we are done